There is a machine parked in a California rail yard that gets used roughly 5 times a decade. It was built in the 1920s. It cannot move under its own power. It weighs nearly 150 tons, and for years at a stretch, it does absolutely nothing except sit under a tarp while newer equipment rolls past it. And when the mountain finally does what the mountain does, when the snow comes down in a way that stops a transcontinental railroad cold, this 100-year-old machine is the only thing on the property that can fix it. Not the newest locomotives, not the modern maintenance fleet. This. Which raises an obvious question. In an industry that has replaced almost everything else twice over, why is the answer to 20 feet of snow still a design that predates the automobile? To understand that, you have to understand what snow actually does to a railroad, because it is not the problem most people assume it is. A locomotive is heavy, absurdly heavy. The instinct is to think that a machine weighing 200 tons should simply drive through a snowdrift the way a ship drives through water, and for the first few feet it does. Loose powder gets pushed aside without much argument. The trouble starts when the snow has somewhere to go, and then suddenly doesn't. A railroad through mountains is not a flat line across a field. It is a sequence of cuts, blasted through rock, embankments raised above the terrain, and shelves carved into hillsides. In a cut, the track sits at the bottom of an artificial canyon with walls on both sides. Snow falls into that canyon. Wind blows more snow into it from the surrounding slopes, and what accumulates there is not the snow that fell on that spot. It is the snow that fell on everything upwind of it, funneled and packed into a trench with vertical sides and no exit. That is how a mountain railroad ends up with drifts 3 and 4 times the height of a locomotive. And here is the part that defeats the obvious solution. Snow that has been packed by wind, warmed by afternoon sun, and refrozen overnight is not fluffy anymore. It has the structural character of hard styrofoam, and in the wet coastal ranges, it turns into something closer to wet concrete. Railroaders in the Sierra Nevada have a name for it. They call it Sierra Cement, and they are not being poetic. So the early railroads did the only thing anyone could think of. They built a wedge. The bucker plow was a blunt instrument in the most literal sense, a huge wooden or steel wedge mounted on a car frame, tall enough to hide the locomotive behind it, designed to split a drift down the middle and shove the halves to either side. The physics were simple. Momentum in, snow out, which meant the technique was equally simple. You backed the plow train up, you got a running start, and you hit the drift as fast as you dared. It worked. Sometimes. The rest of the time, it produced exactly what you would expect from throwing 100 tons of iron at an immovable object. Buckers derailed constantly. Crews riding the plow were thrown around inside a wooden box with no meaningful protection. And there are accounts from the 1870s of men being tossed under the wheels of the very locomotive, pushing them and surviving through nothing but luck. 4 to 10 locomotives might be coupled behind a single bucker depending on the depth ahead, all of them accelerating into a wall of snow with no reliable way to know what was inside it. And when the wedge finally stalled, which it always eventually did, the railroad fell back on the oldest tool available. Men with shovels. That is the detail that gets lost in the romance of the transcontinental era. Before mechanized snow removal existed, clearing a mountain line meant hiring crews to dig it out by hand, sometimes shoveling snow into empty boxcars so it could be hauled down the mountain and dumped. It was brutal, freezing, and frequently lethal work, and it was performed disproportionately by immigrant laborers whose names mostly did not make it into the company records. Some of them died in the drifts. Some died when the snow sheds built to protect the tracks collapsed on top of them under the weight of a heavy season. The railroads knew this was unsustainable. They just did not have an alternative. The alternative, when it came, arrived from a direction nobody in the industry was watching. It came from a dentist. In 1869, a Toronto dentist named J.W. Elliott patented an idea he called a revolving snow shovel. The concept was elegant and for its moment completely impractical. Instead of pushing snow, you would cut it, lift it, and throw it. A spinning wheel would chew into the drift and hurl the debris clear of the right-of-way entirely. Elliott built a small, hand-operated model to demonstrate the principle. He never built a full-size machine, never found a railroad willing to fund one, and eventually let the idea go. It sat dormant for roughly 15 years. Then a machinist and mill owner from Orangeville, Ontario named Orange Joel picked it up. Joel had the mechanical instincts Elliott lacked, and more importantly, he had a workshop and the patience to iterate. Through the winter of 1883 and into 1884, he built working models and tested them, using sand as a stand-in for snow because sand let him measure how much material a given blade arrangement could actually move. His key contribution was recognizing that one spinning wheel was not enough. Snow that has been packed hard does not feed smoothly into a fan. It jams. So Joel put a cutting element in front, arranged to break the face of the drift apart, and a throwing element behind it, arranged to take the loosened material and launch it. Cut first, then throw. 2 jobs, 2 mechanisms, 1 shaft. Joel secured his patent in 1884 and then did the thing that separates inventors from footnotes. He found people who could build it. 2 brothers with a machine shop in the same town, John and Edward Leslie, agreed to construct a full-size working prototype. By April of 1884, the machine was finished and being tested in a nearby rail yard. It worked, and the Leslies, seeing what they had in front of them, bought the manufacturing rights outright, moved the operation to New Jersey, and started building. What they built looked less like railroad equipment than like something that had wandered in from a different industry. Picture a boxcar. Now picture the entire front end of that boxcar replaced by a steel wheel roughly 10 to 11 feet in diameter, fitted with curved blades, mounted so that it faces directly into the direction of travel. Behind the wheel sits a chamber. Above the chamber sits a chute that can be swung to the left or the right. Inside the car body is the power plant. In the early machines, that meant a boiler and steam cylinders, an entire locomotive's worth of machinery devoted to one job, turning that wheel. And this is the detail that surprises almost everyone who learns it. The rotary does not drive itself. It has no traction motors and no connection between its engine and its wheels. Every ounce of its power goes into the cutting head. Forward motion comes from locomotives coupled behind it, pushing, which sounds like a design flaw and is actually the whole point, because it means the machine no longer needs speed. The wedge plow required momentum, and momentum is what made it dangerous. The rotary can crawl. It can approach a drift at walking pace, a slow, deliberate speed that gives the operator time to read what is in front of him and gives the pushing locomotives time to stop if something goes wrong. On a mountainside shelf with a 1,000-foot drop on one side, the difference between hitting an obstruction at 30 miles an hour and touching it at half a mile an hour is the difference between a bad day and a funeral. The operator sits in a cab above and behind the wheel with control over 2 things that matter: how fast the blades turn and which way the chute is aimed. That second control is not a convenience. On a 2-track line, you throw the snow away from the adjacent track, or you have just buried the route you were trying to keep open. On a mountainside, you throw it downhill. In a cut with walls higher than the machine, you throw it as far as the fan will send it and hope it clears the lip. A modern head can spin at speeds high enough to throw wet snow well past the ditch line, and the effect from a distance is genuinely strange. There is no visible pileup, no bow wave. The drift simply disappears into the machine and reappears as a white arc 100 feet away. The productivity difference was not incremental. Contemporary accounts held that a rotary could accomplish in 1 hour what a conventional plow needed a full day to do. Railroads noticed. In 1888, a Canadian transcontinental fitted the design to a group of locomotives for service in the Rockies, adding scoop-shaped flanges to the wheel because the wet-packed snow of the Mountain West behaved differently than the dry powder of the prairies. Orders came in from across North America and from Europe. And then, in a twist that reads like a novel, the man who started it turned on his own machine. Orange Joel and the Leslie brothers fell out. The Leslies had accumulated a stack of their own patents, covering improvements to the design, none of which credited Joel. So Joel went back to his workshop and built a competitor. Instead of a bladed wheel, his new machine used a massive conical screw, a corkscrew mounted at an angle that would auger into the drift and drive the snow up and out through a chute above. In April of 1890, the two designs met head-to-head. The venue was a narrow gauge line in the Colorado mountains, near a tunnel more than 11,000 feet above sea level, in conditions that would have destroyed either machine on a bad day. Two competing answers to the same question, running against the same drifts, with the trade press watching. The bladed rotary won. Joel's screw excavator was not a failure exactly. It moved snow, but it moved snow less reliably in the conditions that actually mattered, and the market delivered its verdict quickly. Roughly 11 of the screw machines were built across 2 years. By 1900, close to 60 of the bladed rotaries were in service, and the basic architecture Joel himself had sketched in a Canadian workshop had become the industry standard under someone else's name. If you're finding this worth your time, consider subscribing. We cover railroad engineering and the machines behind it every week. Now, everything to this point makes the rotary sound invincible. It is not. And the specific ways it fails explain almost everything about how these machines are used today. Start with the obvious one. A rotary snowplow is a very large blender pointed at terrain it cannot see into. Snow that fell out of the sky is clean. Snow that came off a mountainside in an avalanche is not. It arrives mixed with rock, broken timber, torn up ballast, fence posts, and whatever else the slide collected on the way down. And a blade assembly engineered to shear through packed snow reacts badly to a boulder. Modern machines are built to pass a rock of maybe 25 pounds out through the chute without catastrophe, but that same rock can still chew up a blade, and anything larger can stop the head outright and wreck it. This is the reason rotaries were never universally adopted. Out on the northern plains, where the snow is deep but the terrain is empty, the machine performs almost perfectly. In the mountains, where the deepest snow is, everything is fine right up until the moment the rocks and the trees show up. Then there is speed, or the absence of it. In heavy snow, a rotary works at just over half a mile an hour. Slower than walking, push any harder and the blades clog, the throat packs solid, and the machine stops itself. In the coldest conditions, the head can freeze outright, at which point the crew climbs out on top of the plow with brooms and hand tools and chips the ice off by hand, in the weather, on a mountain, in the dark. And when the drift is taller than the machine, the technique becomes something closer to mining than plowing. The crew pushes the rotary forward into the face until it has bored a tunnel as deep as it can safely go. Then they back the whole train out. Then they wait for the roof of that tunnel to collapse into the trench. Then they go in again and clear what fell. Forward, back, wait, repeat. For hours, sometimes for days. Crews assigned to rotary work pack accordingly. Extra gloves, extra outerwear, their own food, their prescription medications, charging cables, and cash, because there is no reliable way to know when the assignment ends or where you will be sleeping when it does. And sometimes the machine sent to rescue the railroad becomes the thing that needs rescuing. In January of 1952, a Sierra Nevada line was fighting a storm cycle that had already pushed its equipment past its limits. Rather than shut the mountain down entirely, management chose to run priority trains behind the plows. One of those trains was a westbound streamliner carrying 226 passengers and crew, which left the summit late on the morning of the 13th and ran into an avalanche that had come down after the plow ahead of it had already passed. The train stopped, and then the mountain kept snowing. There were no radios between stations. A track supervisor riding in the locomotive cab put on his boots, climbed down into the storm, and walked to a telephone to report what had happened. Help came fast. A rotary and a cab-forward locomotive worked their way down the grade, plowed past the stranded train on the opposite track, crossed over, and plowed back to it. Crews hand-shoveled the last few feet between the machines so they could couple up. Then they tried to pull the train out, and it would not move. Then an air pump failed on the plow, and the plow stopped working. Over the days that followed, the rescue effort disabled 5 rotaries. 2 were trapped by later slides, and 1 was hit directly. The engineer running it, a man who had nearly reached the stranded train, was buried when the slope above him let go. Others watched it happen and could not get to him. It took days to recover his body. The passengers came out on the 3rd day, hauled through the snow to a highway and eventually to Oakland, cold and hungry and mostly unhurt. The train itself sat in the drifts for weeks afterward. What changed after 1952 was not the machine, it was how the machine was deployed. The practice that became standard on that mountain was to build a plow train with a rotary at each end, heads facing outward, locomotives sandwiched between them. Because the lesson of that January was not that the rotary was too weak. It was that a rotary facing forward has no answer for a slide that comes down behind it. With a head on both ends, the train can always cut its way back out of wherever it just cut its way into. That configuration is still used today. Which brings us to the strangest part of this story, which is that these machines never really got replaced. The rotaries working the American mountain passes now are, in many cases, the same car bodies that were built in the 1920s. What changed is what lives inside them. The boilers came out. Diesel engines and electric drives went in during the middle of the 20th century, which eliminated the water stops, the coal, and the firemen, and left a machine that could be started in the morning by one person. Multiple unit control was added so the operator in the plow cab could command the locomotive shoving from behind, instead of relying on whistle signals to a crew 100 feet back with no view of anything. The steel around all of that is largely original. A machine in service today might carry a build date from the mid-1920s on its frame and a prime mover from a completely different era in its belly. There are not many of them. One Western railroad maintains what is generally considered the largest surviving fleet in the country, and that fleet is measured in single digits. Another Class 1 keeps a handful, rebuilt from machines originally constructed for 2 northern railroads early in the last century. That is essentially the national inventory. A few working machines, a few more in museums, and nothing new being built. And the reason nothing new is being built is not sentiment. It is arithmetic. A rotary is capital equipment that earns nothing. It hauls no freight. It generates no revenue on its best day. It exists to prevent a specific, rare, extremely expensive failure. A mountain crossing closed for a week, with traffic backed up across half a continent behind it. Some winters it never leaves the yard. In others, it runs a handful of times, and each one of those runs might be the difference between a railroad that is operating and a railroad that is not. When the deepest snowfall seasons come through, the machines get called out, sometimes clearing snow measured in dozens of feet across a single winter. And the crews who run them are working from knowledge that mostly is not written down anywhere, because you cannot learn how a rotary behaves in wet snow from a manual when the machine gets used 5 times in 10 years. So the railroads keep them. They keep them because the geometry of the problem has not changed since 1884. Snow still falls into cuts. Cuts still have walls. The snow still has to leave the right-of-way entirely rather than being piled beside it, because piled snow just blows back in. And the only mechanical answer anyone has ever found to that specific problem is to cut it, lift it, and throw it somewhere else. Everything around these machines has been reinvented. The locomotives pushing them are computer-controlled. The dispatchers routing them work from screens hundreds of miles away. The freight in the trains waiting behind them was tracked by satellite before it ever reached the mountain. And at the front of all of it is a steel wheel with curved blades, doing exactly what a dentist sketched out in 1869 and a millwright made real in a Canadian workshop in 1884. The next time you see footage of one of these things working a pass, watch what it does with the snow, not the machine, the snow. Watch the white arc leaving the chute and disappearing over the bank, and understand that you are looking at the entire idea. Not strength, not speed. just the recognition, made by someone who had never worked for a railroad, that the answer to an immovable object was never to hit it harder. It was to take it apart a few inches at a time and throw it away.